Thanks for coming, everybody. So this talk is about enforcing mTLS using Linkerd and OPA Gatekeeper. Just by way of giving us a chance to get to know you folks better, how many of us are currently using Linkerd? By a show of hands, a number of you. How many of you are currently using OPA Gatekeeper? Okay, great, cool. You folks are in the right place. So here's the outline for the talk. We're going to start off by presenting a very high-level description of the problem and solution that the rest of the talk is going to focus on. And then we are going to break the ice a bit by introducing ourselves. Then from there, we're going to spend a very short amount of time talking about why use Linkerd for your mTLS stuff. And then we're going to dive into a time of demo where we will use Linkerd to roll out mTLS on a Kubernetes cluster. And once mTLS is rolled out, we will use some OPA Gatekeeper to define and enforce mTLS policies during workload emission. And finally, we're going to conclude with some closing thoughts, and there will be a time of Q&A towards the end. So all of us come to KubeCon because there is a set of problems that we really want to solve. I assume the reason you are here this afternoon is because one of the problems you need to tackle revolve around securing east-west traffic within your Kubernetes clusters with encryptions and identity-based authentication. So there are a number of things that you need to take into consideration when securing like in-cluster service-to-service communication. But we believe mTLS is going to play a very crucial part in that part of your security journey.
So this is Ivan Sim. He is a software engineer at Buoyant, and he is also a Linkerd contributor.
And sharing the stage with me this afternoon is Rita Zhang. She's a software engineer from Microsoft, and she's a maintainer of the OPA Gatekeeper project. So what is mTLS? Mutual TLS, not to be confused with multiplex TLS. To put it simply, it's that process where two entities try to confirm each other's identity using TLS certificates. Now, we can all read about the details of mTLS in the TLS RFC under the TLS handshake protocol section. But again, to put it simply, mTLS introduces a number of additional steps into the well-known TLS handshake process, or protocol rather, whereby the server, after issuing and responding with a server hello request and the server certificate, it also issue a request to the client and say, hey, wait a minute, before we continue, show me your client certificate. And after both parties receive each other's certificates, they will attempt to verify and confirm each other's identity by checking the digital signatures within the cert. Are you who you claim you are? So drawing from personal experience, rolling out mTLS is not as simple as one would hope. Not surprisingly, though, the problem is not usually non-technical. From my personal experience, like rolling out mTLS involves challenges around keeping track of all the assets, the keys and the certificates. Where did they come from? Who created them? And when they were created, what sort of configurations went into the tools? Can you trust the tools? If the assets are stored in vaults, who have access to those vaults? And when the certificate signing request was first issued, what sort of settings went in there? The other challenge that I have personally experienced is getting everyone on board. Say you have service A trying to talk to service B via TLS. Can we ensure that they both got rolled out at the same time? If service A is TLS and the other one doesn't, there needs to be some sort of stopgap solution in between. But for how long? For how many releases? And for those of us who manage and implement our own certificate authority solution, I'm sure we can appreciate the amount of time and effort goes into maintaining these components. What if there are vulnerabilities within your CA solution? How would fixing and patching that affect the rest of your production workload? So why use Linkerd for mTLS? Why trust Linkerd? Well, for one, I'm biased, but I do think Linkerd is secure. Just a couple of months ago, Linkerd passed a penetration test and security audit, code audit, conducted by a third-party company, security company, sponsored by the Linux Foundation and CNCF. And the team is proud to share that we passed the test with flying colors. And you can read about all the details of the audit in that link there. And in addition, Linkerd also provides a simple and consistent way to roll out mTLS. A workload is either in the mesh or not in the mesh. And there's only one way to opt in, and there's only one way to opt out. And mTLS is enabled by default with zero config, so no YAMLs. And you guys may have noticed that this morning during the keynotes, in the next couple releases, we are going to make mTLS a mandatory thing. And it will work by default, and it will continue to work by default, and it will continue to work seamlessly for all your workloads. Linkerd is also very scalable. I know of one user in our community who is using Linkerd to support a production workload of 3,500 pods. And all of them are injected with the Linkerd proxies, communicating via mTLS. So what is Linkerd? It is an open source service mesh solution for Kubernetes. It is a CNCF project, and it offers an array of really cool features. For the purpose of this talk, we are just going to focus on the automatic mTLS part. So we're going to switch over to a demo time. During the first part of the demo, we are going to deploy two namespaces. On the left is the Linkerd control plane namespace with all the Linkerd control plane pods in there. And to the right, we are going to deploy an insecure emoji application made out of 4 deployments. And then we are going to use something called ksniff to perform a man-in-the-middle interception to sniff the traffic that goes in and out of the web component. And then we're going to secure the insecure emoji application by injecting the Linkerd proxy. And then we will see how the mTLS got automatically deployed and secure and encrypt all the traffic. I'm going to switch over to my terminals now and run demo time and run our script. I want to make sure I am connected to my Minikube instance. Yeah.
All right, so first, let's deploy the blue emoji app. And as you can see, first we dump a bunch of components that is part of the application. And as the pod is coming up, next we're gonna actually install Linkerd in the cluster for the very first time. And as you can see, Linkerd has a really nice install CLI and one command and you get everything out of the box, which is really nice. So here, we're going to run the control plane status command just to check the status of all the Linkerd components, make sure they all come up successfully.
It's the terminal. I think it's a bug in the K console. If I enlarge this, if I change the font size, it keeps repeating the standard output here. But I assure you, this is waiting for the Prometheus container to come up. So while this is happening, I can show you guys what that the emoji application looks like. I think we are at localhost 8080. So again, nothing surprising there. It's just an application that with a web front and 2 backends that allows us to vote for our favorite emojis. And one of the donut emoji is intentionally broken just to generate some faults and errors in there.
All right, let's come back. OK, all the control plane components are all up and running. Next, we're going to use ksniff, which is a kubectl plugin that allows us to use TCP dump and Wireshark to actually look at the traffic from our pod, and we can actually sniff the traffic. That allows us to actually see the payload, and if I'm a bad guy, I should be able to see all this stuff in clear text, right? All right, so this is running. We're going to start up Wireshark, I think.
It's trying to find like all the network interfaces.
Cool. So now you're going to filter the request.
So we're going to look at all the 200 responses that come back from the backends. And not surprisingly, we can see all the data.
Look at that.
Imagine this is your password or your credit card number, but for now it's just emojis. My apologies for those of you at the back. I think like the resolution may not be great. I tried to fiddle around with the Wireshark UI, but hopefully you can see part of it. So I'm going to exit out of Wireshark.
Okay, so next we're going to run Linkerd inject to see if we can actually inject a Linkerd proxy into our application. And this should actually automatically enable mTLS for our service, our components. And as you can see, Linkerd inject actually injects a sidecar proxy container into each component. And as this is updating, we see that it now has 2 containers as opposed to the previous installation has 1. And so now you see the proxy sidecar has been added. So next we're going to use the same sniff command, and now we look at the exact same application, and let's see if we can still get the content from Wireshark.
Going to pause a little bit. So right away you can see all the application data. They are now encrypted, so you can no longer see my favorite emoji being so yeah, and all this happened with just me typing in like the Linkerd inject command and receiving like the deployment YAML of a live deployments.
So how is Linkerd able to do this?
Good question. It's all magic. Nah. It's really simple, actually. So what happened when we run the Linkerd inject command? So reading this diagram from left to right. So when we run like the Linkerd inject command on like a YAML workload, Nginx or MySQL or whatever, the CLI simply annotates the YAML with a special annotation. And that is enough to tell the API server to call into the emission webhook. So with the mutated YAML, we pipe it into kubectl apply, which sends the object to the API server. And the API server takes the Kubernetes object, the object through what we call the emission phase. And during the mutating phase, the API server actually calls out to the Linkerd proxy injector deployment, which is an emission webhook. And the proxy injector takes the object, mutate it by inserting an additional sidecar, which is the Linkerd proxy sidecar, into the object, and return the mutated object back to the API server. And the API server takes that mutated object and allows it to pass through the rest of the emission phase and eventually persists it in SCD. And this whole emission phase, it happens every time when you type kubectl apply or kubectl run. So what happened after a service or an application is injected with the Linkerd proxy? Again, reading this diagram from left to right, as part of the proxy startup process, it will issue a certificate signing request and send it to the identity service, which is the internal certificate authority component of the control plane. So the proxy actually embeds its identity into that signing request, and it also sends along the service account token to the identity service. So essentially, we bind the proxy's identity to the service account that the pod is using. And then the identity service from there will issue an API call to the API server via the token review API. And it says, hey, I just received a service account token. Is it legit? And if the response that goes back to the identity service is positive, the identity service is going to sign the signing request and then issue a TLS cert to the Linkerd proxy. And then and only then will the Linkerd proxy mark itself as ready to send and receive traffic. And by default, the proxy will auto-rotate the TLS cert every 24 hours, and that value is configurable. And it does that by issuing a new CSR every 24 hours. I want to stress that also the private key that was used to sign the CSR is stored in memory, and it lives and dies with the proxy. So it never leaves the container or the pod. Now, so how does the proxy knows about its identity? I mentioned earlier that we bind the proxy's identity with this Kubernetes service account that the pod or the workload uses. So there are a number of environment variables which we define as part of the proxy container spec. So this will tell the proxy, hey, this is your identity local name. It's that second environment variable there. And then this is where you can find the service account token file. This is the trust root that you can use for future communication. And this is the endpoint of the identity service. So just very straightforward. And it's something that you can just look at and debug if something goes wrong. And of course, nothing goes wrong, as we know it. And then what happened now when two injected proxies try to talk to each other? Again, reading this from left to right, if I have a injected foo service trying to talk to an injected bar service, the first thing the foo proxy is going to do is going to issue a lookup request to the destination service in the control plane. And it will say, hey, help me to look up where bar.ns is. And then the destination service is going to issue a call to the Kubernetes API service and say, get me the endpoints and all the pod IP addresses. And it receives that information, and then it packages it up into something that we call service profile, and then send it back to the foo proxy. And now the foo proxy will know, okay, the bar proxy is at 10.0.10.1.2, and they also have some extra information about it. Can the bar proxy participate in TLS, for example? Can it do retries? Are we gonna start doing gRPC load balancing there, that sort of things? So from there, the TLS handshake would just start. So if I were to switch back over to my Minikube cluster right now, and I type in kubectl apply or kubectl run, you will see that I can deploy any and every sort of workload to my cluster. Again, probably what we don't want for our production environment, right? So currently, in Linkerd, there is no way to define and enforce policies saying that only this kind of workload with certain labels and annotations can enter into the mesh or can be deployed onto the cluster. And this is where we feel like OPA Gatekeeper is going to fit in nicely to solve the problem.
All right. So how many of you guys heard about OPA this morning? How evasive it is, right? So we are taking this opportunity to talk about Gatekeeper, which is basically the customizable Kubernetes mission webhook that helps you enforce policies in your organization and also strengthen governance of all the clusters that you have to manage. So again, it's based on OPA, and it is something that is created so that you, the administrator, can create and define your policies via configurations, not code. And let's talk about some of the motivations behind the project. So I know a lot of companies probably have a lot of policies that they have in place, and a lot of administrators really want a way to control what the end users can actually do on the cluster. So this really helps with that. And wouldn't it be nice to also have a solution that helps you ensure your clusters are always in compliance to your company policies? And in any given time, wouldn't it be nice if there's a solution that actually allows you to see, hey, looks like these resources have issues and they're out of compliance, and here's how I can mediate those issues. And last but not least, wouldn't it also be nice to preview the new policies that you have created in the company into a lot of these production clusters? Now, a lot of us actually create policies or there are new policy requests that are created for existing clusters that's been running for a long time. It would be nice to actually be able to test these policies and build confidence before you actually deploy in the cluster and prevent impacts on existing workloads and impacting your end users. And last but not least, wouldn't it be nice to actually make sure that the cluster admins and developers can coexist and be happy together, both ensuring the conformance, but also not sacrificing your agility and autonomy. So that's basically the background behind why the Gatekeeper project was created. We're currently at V3 in the project, and as you can see, this is a diagram of what the project, what the components look like. And again, at the heart of Gatekeeper is OPA, which is the policy agent that actually executes the actual Rego rules that you create. Now today, it is mostly for validating a mission, and it has been implemented to run in your CI. It can be used for your CI/CD pipelines, and the policies are actually written as CRDs now. So what happens is you can then define and create your policies by writing the Rego rules as templates. And you can think of them as functions for your other policies that you're actually going to create instances for. And when you create a policy instance, that's when you actually pass in the parameters for these rules. Now, once all these CRDs are in your cluster, what happens is Gatekeeper then replicates the information to OPA, and depending on how you've set it up, you can also replicate the resources in your cluster into OPA, thus allowing you to do things like referential policies where you are looking for uniqueness, where you're comparing the emission requests versus everything else that already exists in the cluster. And last but not least, as you can see, there's also this audit feature that allows us to periodically query the state of the cluster. And as an administrator, this really helps because then you can see, okay, what are the resources that are out of compliance and what are the resources that are not meeting this particular policy. And also, we've introduced the dry run concept in the most recent release, which really enables gradual rollout to build confidence in the policies that you're rolling out for everybody else. And last but not least, I want to thank Microsoft, Google, Red Hat, CBA, Styra for creating this project, and Replica for donating the Gatekeeper name.
Cool. So right now we are going to continue with the second part of our demo, and we're going to run continue that demo script on the same Minikube cluster. By the way, it's not pre-recorded. It is a real a Minikube cluster. And I have to use Minikube just so that I can get ksniff to run. Otherwise, if I use kind, like container-based Kubernetes, then ksniff won't run. Anyways, tangent. So we are, in the second part of the demo, we are going to install Gatekeeper. And then we're going to install that insecure emoji application again, this time around into a different namespace. And then we will see how Gatekeeper is able to detect there is insecure workload within my clusters because it violated some of the mTLS requirements. And it will raise some audit events. And then we'll see how we can resolve it by, again, injecting those workload with the Linkerd proxy and enable mTLS. I'm going to switch over to my terminal.
All right, so now we're going to install the same application, but now we call it green. And it's going to be deployed in its own namespace. So once it's applied, next all the components are coming up. And next, we're going to install Gatekeeper for the very first time on the cluster. You can grab the YAML, and all the Gatekeeper components are now installed in the cluster. And let's see, all of them are, let's wait to see, make sure they're all coming up. All right. So here what we're going to do is omit some of the namespaces from our policies because we know kube system and gatekeepers are not the namespaces that we care about for this particular policy. And the way we do that is by adding this namespace label that we already know. So once this is done, then we are going to install the mTLS constraint template. So as I mentioned earlier, the constraint templates are really where the Rego logics live. So now the constraint templates are deployed, and next we're going to, let's take a look at what that Rego looks like, right? We talk about it so much. Here, let's see. All right, so let's see. So here we have a CRD, and it actually defines what the policy CRD looks like. So here, as you can see, there's the spec for the CRD for this kind named Linkerd mutual TLS, right? It could be whatever you want. And so with this kind, every other policy instance that you create thereafter will be based on this type, right? And so as you can also see down below is where we have the actual Rego, the logic for how we're defining what the policy is going to look like, what resources it's going to actually process. And as you can see, we have a bunch of spec validations, right? And here's how we know, like, hey, looks like this container doesn't actually have the Linkerd proxy enabled. There's no proxy sidecar running. There's no Linkerd proxy sidecar running next to my application, and it looks like there's no annotation that is required to ensure that Linkerd's automatic mTLS has turned on. And next, there's a bunch of environment variables that we know that is required for mutual TLS to actually be enabled and working, and therefore these are the things that's in the spec that we're looking for, and it's missing. And if any one of these requirements is missing, that's when, if you look at the top, that's when we say, okay, looks like there's a violation, and then go ahead and display this error message to your users so that they know, hey, it looks like you don't have Linkerd inject enabled, and it looks like you don't have an mTLS turned on. So let's actually see how this works in Reals.
Give me a couple of seconds for the CRD to get ready.
Okay. All right, so next we're actually installing the constraint. And as I mentioned earlier, that's where we pass in the parameters, right? Mm-hmm. And so the parameters here, as you can see, we're going at the top, right? This is where we say, okay, for the Linkerd mutual TLS kind, here are the matching kinds that we're going to match on, and we're going to look at pods. And for other policies that you're going to create, you can specify whatever resource you want, right? And then here we are actually going to use namespace selector to just whitelist out namespaces that we don't care about. And then below is actually where we pass in all the parameters that we think Linkerd is actually looking for this particular policy to run. And if you recall from the Regos, these are the actual annotations and environment variables that the Regos logics actually look for. So, cool. Sure.
Okay.
All right, let's see if the application actually gets detected.
The audits part, yeah.
Yeah. So next we're going to describe on the constraint, and this is where we see the audit results. Let's see.
It's way at the bottom there. Oh, there it is.
All right. So here, as you can see, the last audit ran at this time, which is like 30 seconds ago. And then here, all the violations in the cluster are now identified. And as you can see, these were the components in the emoji green application, and they've been flagged as, hey, it looks like you don't have mTLS turned on. Mm-hmm. So how do we actually, now that I know these are the issues, how do I actually get myself out of this? Well, we can inject run the same Linkerd inject command against our green emoji application, and let's see how that works. All right. So now Linkerd does its magic. Now it's going to come up. All right. So now all the mTLS components are there. They've been mutated. Let's see if the audit results actually is updated.
Yeah, so this is a part.
So now the audit just ran, and it looks like there are no violations. So yeah, we're good.
Yeah.
Ready for production?
Ship it.
All right, so here are just some examples of things that we thought that would be cool features for your applications, in terms of securing your services that we didn't quite have time for this demo. So for example, ensuring that you have policies that actually checks, hey, all your applications are actually HTTPS only, making sure that all your ingresses have unique host names, services should have globally unique selectors, and
yeah, so some additional rules that we can implement using Rego is to make sure like that admission request we talked about, like has some sort of user ID being defined in them. So you make sure the workload is actually submitted by someone running kubectl apply with that appropriate the authentication. And at number 5, some of you may have noticed we actually deploy the insecure green emoji application first, then we install OPA Gatekeeper. And we did that on purpose because we want to be able to show off that audit violation events. But in like a real production environment, you probably do it the other way around, where you would install Gatekeeper first, and then you just reject outright anything that is not mTLS compliant. And finally, like Linkerd store like really rich information about the traffic and the matrices in Prometheus, and that include like whether the traffic is TLS or not. So if it is stored in Prometheus, guess what? I can like hook it up to Alert Manager and use that to notify me based on the matrix in Prometheus that, hey, we just detected some non-TLS traffic coming in from this particular source. So yeah, very cool and hands-on stuff that we can all try, but just don't have time for it today.
So 2 different projects together, united, and help where it's here to secure your services.
In conclusion, excuse me. So both Linkerd and OPA like are supported and contributed by like growing and healthy communities. And for Linkerd, you can find us on, I don't know, GitHub, Slack, whatever social media is out there. Come to our monthly community calls and stuff.
And for OPA, there are various ways of reaching out. There's Slack with us, so OPA, Open Policy Agent has its own Slack. There's also Kubernetes policy channel in there. We're always hanging out there, so if you have questions, feel free to ask. And of course, open issues, and we're always looking for feedback to make this thing better. And we have a weekly Tuesday at 2 p.m. Call if anybody wants to join.
Well, with that, thank you very much. Do we have time for questions?
How about we can do 3?
All right, 3 questions. Yeah. Made it count.
And if you enjoyed this talk, there's a way to rate it from the schedule, so go and give it a happy face. And give feedback, which the presenters can see later. Any questions? There's one.
Hi, is there any solution for hybrid environments? Like, for example, I have Kubernetes and a bit of workload running outside Kubernetes. So can there be a hybrid solution covering both of them?
Yeah, currently, like for external resources, like those are, because it's outside of the mesh, so Linkerd is, at the moment, doesn't look after securing those traffic. So it'd be up to your application to, because like also like if it is using like a different kind of cert, the Linkerd proxy won't be able to see it, right? Because it's all encrypted, unless it meant in the middle of your traffic, which is not good.
Once the policy changes, or once Linkerd does mTLS by default, would the policy need to change from what you showed here to still track for that?
No, the policy stays the same. Well, as long as like the policy author, as long as that gets updated per the policy you want to apply or enforce. The policy just enforces at emission time, which we didn't get to show, but essentially once you're out of the gate or whatever, then the audit results won't catch it. So if you had like a way to raise alerts, it won't even come up.
If I wanted to use mTLS to lock down communication, so like service A can only talk to B, but A can't talk to C, is that something like Linkerd D? We could use mTLS therefore, or would that have to be something that follow like into the OPA space?
So that's a good question. Like I think so. Right now, like Linkerd D out of the box doesn't support like endpoint authorization. So usually like when users bring that up, we would ask them would network policies with labels and selectors and IP addresses help with it. But if they want something more fine-grained, like I think eventually it will require some sort of policy enforcement and a partnership of some sort between Linkerd and
Yeah, this
OPA.
also came up when we were doing this talk. It's actually something we want to explore further, but currently there is no way that we are aware of. Yeah.
We're right at time, but I think we can do a couple more. If anybody else, does anybody else have any other questions? Awesome. Thank you so much, guys.
Thank you.